In this video, we're going to go through some work on exact values, and I've got the slide on the screen. This is directly from your notes. This is the slide that we're starting from, but just so that you're aware, in this video and in today's lesson, we're just going to focus on 14b and 14c, and we'll cover 14f next time. Okay, so just for now, we'll look at 14b and 14c. And from this slide as well, that actually means that we're looking more at the unit circle here. These two triangles we won't really worry about until the next lesson when we do cover 14f. So basically the idea is that we should be able to find sine, cos and tan of particular angles without needing to use a calculator and without needing to use an approximation. So probably if you think back to year 9 and 10 trigonometry, most of the time when you had to work out sine, cos and tan of an angle, you'd type it into your calculator and you'd get a really long decimal and you'd just round it off. But there are certain angles where we can work out exact values. And we can work out exact values for angles like 0 degrees and 90 degrees. We can also work them out for 30 degrees, 60 degrees and 45 degrees, but that'll come later on. But particularly today, what we're going to look at is how you find these exact values when the angle is 0 or any multiple of 90 degrees. So we're going to focus on the unit circle in this section. So just coming back to this idea of the unit circle, here's a picture of one. Remember, the unit circle has a center at 0, 0 on the Cartesian plane and a radius of 1. And the big idea I want you to remember from last time is that we read values of cos of theta from the x-axis. So you can actually label the x-axis as cos theta and the y-axis as sine theta. So when we're moving around the unit circle, on any particular point of the unit circle, wherever you are, whatever any position on the unit circle, the x-coordinate of that point will tell you the value of cos theta, and the y-coordinate will tell you the value of sine theta. And we won't go through it in full detail again, but that was because when we said, well, if we just pick a point somewhere on the unit circle, remembering that we measure the angle from the positive x-axis anti-clockwise, so going this way, if we call that angle theta, what sort of happens when we look at this point is if we drop a line down to the x-axis there, we actually form a right-angled triangle. And because this is a unit circle, the hypotenuse is 1. And so that means that when we look at the opposite side, that's going to be given by sine theta, because we would get sine theta equals opposite over hypotenuse, but really it just becomes sine theta equals opposite over 1. So the opposite side is actually sine theta, which is the vertical side. Hence the y values hence sine theta comes from the y values. And if we're considering the horizontal distance, it's going to be cos theta equals adjacent over 1. And so therefore cos theta equals the adjacent side, which is the horizontal distance. So main thing to keep in mind there, cos theta we read from the x-axis, sine theta we read from the y-axis. I'm actually just going to go to a different screen here and show you an interactive graph. So this is just the unit circle, but something that we can actually play around with. Now, keeping in mind that the values of cosine are going to come from the x-axis and values of sine are going to come from the y-axis, just watch what happens here as we pick particular points around the unit circle. So firstly, just to show you how this works, at the moment, the point that's highlighted is this point here at 1, 0. And that really means there's an angle of 0. We haven't actually moved any amount of turn around the unit circle. But as I play around with this slider up here and go from a equals 0 to angle equals 30, 40, 50 and so on, you can see this point starts to move. So if I just set it there at about 40, you can see that's what's happening is that we've got a point highlighted. Now this point sitting on the circumference of the unit circle, it's got an x-coordinate and a y-coordinate. Now at the moment the angle is 38 degrees, right? So what this coordinate's actually telling us is that, well, cosine of 38 degrees is actually the x-coordinate of this point. This point has an x-coordinate of approximately 0.79. And you can see down here, that's actually sort of telling us what this means. It means that cos of 38 degrees equals 0.79. And you could type that into your calculator, and it won't be exactly 0.79, but to 2 decimal places, that's what it will equal. And then the y-coordinate of this point is 0.62, this point on the unit circle. And remember, the y-coordinate represents sine theta. So that's telling us that sine of this angle, sine of 38 degrees, would equal 0.62 if we round it to 2 decimal places. And as we sort of use this interactive to move around the unit circle, you can do that for any angle. This one's set to go from 0 to 360 degrees, right? So what you might also notice as we just play around with even rough values here is once we get to an obtuse angle, so at the moment the angle's 116 degrees, notice that over here now the x-coordinate is a negative value because we're on the left-hand side of the graph, and the value of cosine becomes negative. Sine stays positive because sine comes from the y-axis, but cos is now negative. And we talked a little bit in the last lesson about how sine is positive in the second quadrant, but the others, cos and tan, are negative. As we move to the third quadrant and we start to get into reflex angles like 218 degrees, again, you can see we've still got this x and y coordinate, but now both sine and cosine are negative because we're on the left-hand side of the graph and the bottom of the graph, so x and y values are positive. Now this little interactive doesn't have the value of tan, but remember that tan is equal to sine over cosine, so tan would be positive in the third quadrant, but sine and cosine are negative. As we keep moving into the fourth quadrant, we can see that, well, our x values are becoming positive again. So cosine is now a positive value. The x coordinate is positive. And sine is negative. Okay, so let's go all the way back to 0 degrees, because what we want to be able to do is evaluate sine, cos, and tan of certain angles without having to use a calculator. So if the angle is 0 degrees, what you'll notice here is that the point on the unit circle where we've kind of stopped is at 1, 0. Now that actually tells us that cosine of 0, so let's start with the x-coordinate, cosine of 0 is actually 1. Cos of 0 is equal to exactly 1. And sine of 0 is equal to 0. And that's just because we're reading this directly from the x-coordinate, which gives us cos, and the y-coordinate, which gives us sine. As we move a quarter turn, so as we get to 90 degrees, we can see on the unit circle pretty easily that that's going to have, that position is coordinates 0 and 1. And so again, the x value gives us cosine, y value gives us sine. So this is telling us that if the angle's 90 degrees, well, sine of 90 degrees is 1, because that's the y coordinate. Cos of 90 degrees is 0. And you can do this for all the multiples of 90 degrees. So 180 degrees, the point on the unit circle there has coordinates -1, 0. So cos of 180 is -1. That's the x-coordinate. Sine of 180 equals 0. Now, you get pretty good as you use these a lot. You'll kind of potentially start to memorize these, but you can always come back to the unit circle to see why the values are what they are for any multiple of 90 degrees. So if we set it to 270 degrees, we get cos of 270 is 0 because the x-coordinate's 0. Sine of 270 is -1 because the y-coordinate's -1. And as we make our way through a full term, well, when we get to 360 degrees, it's actually just the same thing as if it was 0 degrees, right? Because we're back to 1, 0. So sine of 360 is 0, and cos of 360 is 1, because we're just reading those from the x and the y coordinates. Now, this was set up in degrees, but of course it would work exactly the same way in radians. If it was in radians, we just need to remember that we go 0, then, actually, I'll match it up. So we start at 0, 90 degrees is equivalent to pi on 2 radians. 180 degrees is pi radians, 270 is 3 pi on 2 radians, and 360 degrees is 2 pi radians. So as long as we can remember those equivalents, we can work out, things like sine of pi or cos of pi on 2, and so on. Right, so just flipping back to the slides here, we can see we've got, now this next slide, I'm saying let's skip this for now. We'll come back to this when we look at these triangles, these other angles, but for now we're just going to focus on the unit circle questions. So here we're being asked to find, without using a calculator, find these different exact values. Sine of 90 degrees, cos of pi, tan of 3 pi on 2. Now what I'm going to do is I'm just going to add a couple of extra slides in so I can spread these out a bit and make the unit circle picture a bit bigger. So let's just start with sine of 90. So sine of 90, play around with some colours here. So sine of 90 degrees, really all we have to do to evaluate this is find 90 degrees on the unit circle. So starting from 0 degrees and going around to here. So we know that sine of 90 degrees is this position here. And if we're finding sine of 90, we just need to think, okay, well, sine comes from the y-axis. So at this point here, make it really clear, what is the y-coordinate? And the y-coordinate is 1. So sine of 90 degrees is equal to 1. Right, so anytime you get a question like this, you could quickly sketch a unit circle. It doesn't have to be that neat. And just use it to help you find what the coordinates are going to be. Cos of pi. So if we look now at cos of pi, well, pi, obviously that's in radians, but we know that pi is equal to 180 degrees. So basically what we're going to do is imagine moving around the unit circle till we get to 180 degrees. And we obviously stop here. And for cosine, we're looking for the x-coordinate, because cos is read from the x-axis. So cos of pi is equal to our x-coordinate here, which is -1. Okay, part C, this one asks for tan of 3 pi on 2. Now, tan's a little bit trickier, right? We said that cos comes from the x-axis, sine comes from the y-axis. Tan doesn't really come directly from the x or y-axis, but what you'll hopefully remember from last time is that tan of a particular angle is actually equal to sine of that angle divided by cos of that angle. So to work out tan of 3 pi on 2, we can actually work out sine of 3 pi on 2 over cos of 3 pi on 2. So again, the method here is to firstly figure out our kind of where our angle takes us to on the unit circle. So we start from 0 and we go all the way around to 3 pi on 2, remembering that 3 pi on 2 is equivalent to 270 degrees. All right, so we're this is our spot on the unit circle. And now we just read the x and the y coordinates. So sine is the numerator, sine's on top here. So sine comes from the y value, which is -1. Cos of 3 pi on 2, well, that comes from the x coordinate at this position, which is 0. And of course, anything divided by 0 is going to be undefined. So for this particular value, or of a tan of 3 pi on 2, we actually get an undefined result. Now, I'm going to try my best to write neatly here, but I might just write undef, and you'll know that means undefined. Okay, so anytime that cos is equal to 0, actually tan is going to be undefined. Now that, of course, won't happen at all points around the unit circle, but at this particular point, that's how it happened. But generally speaking, if you need to evaluate tan of an angle like this, any multiple of 90 degrees, you can use this sine over cos method. Okay, couple of quick extra notes. Now these aren't actually in your handouts. I've added these in, but just so that you'll kind of be familiar with them when they come up. Negative angles. Negative angles can actually be used on the unit circle, and it seems a bit funny, but essentially a negative angle just means you start from 0, but you kind of move backwards around the unit circle. You move clockwise instead of anti-clockwise. But really what you're kind of focused on is where you'll stop on the unit circle, what position it'll be in, and that's how you'll work out your exact values. So for example, -60 degrees is equivalent to 300 degrees on the unit circle, because if you went backwards by 60 degrees, you'd end up in the same position as if you went forward by 300 degrees. You can almost imagine it like you're walking laps of an oval or something like that, and it's just really about what position you stop at. Similarly, negative pi on 2 radians is equivalent to 3 pi on 2 radians. It's like if you go backwards by a quarter of a lap, it's the same as going forwards by 3/4 of a lap. And if you had to work out, for instance, sine of negative 359 degrees, that would be equal to sine of 1 degree. Okay, so let's kind of have a look at how this might work if you had to find sine of negative 90 and cos of negative 90. Let's start with sine of negative 90. Well, again, what we'd have to do is think about where do we get to on the unit circle. Now, we're starting at 0 still, at an angle of 0, but if we're going backwards by 90 degrees, we're actually going to come around to this position. So this is the position on the unit circle. And so for sine and cos, we just read the x and y coordinates again. So for sine of negative 90, it's the y value, which is -1. And for cos of negative 90, it's the x value, which is 0. Right, so the negative angle, all it does is just change the direction that we move around the unit circle, but otherwise the method for working out these values stays the same. The other thing that you might come across with exact values is angles that are bigger than 360 or bigger than 2 pi. So it seems a little bit backwards, but essentially the unit circle can keep going and going and going. You can do multiple laps around the unit circle. So basically, anytime you see an angle that's bigger than 360, think of it like you've done one full lap or one full cycle, and then you're just continuing and keeping on going. So for example, if you had to think of an angle of 370 degrees, it's basically just like doing a full loop and then an extra 10 degrees. So 370 degrees is equivalent to 10 degrees. Similarly, 3 pi is equivalent to pi, because 3 pi is really like doing 1.5 laps, and pi is like doing half a lap, but they both take you to the same spot. And if you had to work out cos of 390 degrees, that would be equivalent to cos of 30 degrees, because 390 degrees means you've done one full cycle and then you just went an extra 30 degrees. So again, a quick one just to sort of show how this... oh, hang on. Well, that wasn't the example that I wanted. Give us 2 seconds. I'm going to change this. Let's say we have to find sine of 450 degrees. Sorry, I hadn't changed that example properly. All right, so 450 degrees. Let's think about this. 450 degrees would be like going, well, one full lap, right? 360 degrees, but then continuing for an extra 90 degrees, right? Now, you don't have to write this out, but I'm just sort of putting it there to show it. So what's really going to happen is it's like we've started at 0. We've gone around a full lap. That's 360 degrees. We're now going to go an extra 90 degrees. I'll do it in a different color. An extra 90 degrees. But the key point is that we're going to stop at this position here. And so if it's sine of 450 degrees, well, if that's the position we've stopped, sine we read from the y-axis. So sine of 450 degrees is equal to 1, right? It's the same as if you had to work out sine of 90 degrees.